This video is going to be about the conservation of momentum, still in two dimensions, but this time we're looking at inelastic collisions. Now, I apologize because the words are obviously very similar, and I was pretty confused for a little bit when I was making some of the Google Classroom stuff. It should all be fixed now, but just to be clear, we're going to talk about inelastic collisions now. The stuff you were doing previously where, for example, two billiard balls might bounce off each other, or they might, they kind of go their own separate way. Those are elastic collisions. And elastic means they rebound off each other. They bounce off. And there's no energy lost in an inelastic collision. We are going to talk about inelastic collisions today. Inelastic collisions are those which are objects kind of, instead of bouncing off of each other, objects hit and sort of stick together. It's almost like they become one new object. And let's look at an example. Now what you're going to find is after having done those elastic collisions in two dimensions, inelastic is going to be pretty simple. It's going to be a lot simpler just because there's less to keep up with. You don't have to worry about, okay, well, there's going to be one object after they collide, basically. Alright, so you have here 2 kilogram slab of clay is thrown 2 meters per second north, and another slab of clay with a mass of 5 kilograms thrown 3 meters per second west. These slabs are going to collide and stick together, find the velocity of the new slab. So what I would do is I would draw a picture here. Just because there's a lot of information there, and this is the best, most efficient way to see that. So you have 2 kilogram slab of clay is going 2 meters per second north. Okay, and then it says there's another one that's 5 kilograms is going 3 meters per second west. Alright, so this one's a little bigger, 5 kilograms, and it's going 3 meters per second west. Now these two different slabs of clay, they're going to collide together. And as you might imagine, if you took some slab of clay, if you've ever done any like pottery or, I don't know, played cranium or something, I don't know, play with Play-Doh, when these things hit together, they're going to be kind of sticky. And in fact, we're going to assume here that they collide in a perfectly inelastic collision. In other words, they are going to smash together, right? So afterwards, it would look like this. Ooh. Well, sorry, I don't have the. I was gonna make it look more interesting, but I don't have the right colors. I can't make it look interesting. Anyways. Okay, so they're gonna collide together, and I'll just make it black over here. So after they collide together, they're gonna have basically it's like one new object. Of course, you could imagine they're like probably not gonna be one whole spherical object, but it doesn't matter because we only care about the mass, not really the distribution of the mass. So this new object is gonna have a mass of 7 kilograms because, well, it's just 5 plus 2, 7 kilograms afterwards. And we don't know which way it's going to go. Now you might imagine it's probably going to go something like this, because hey, it was going north, it was going to the west, so it's probably going to go like northwest now. But we're going to look at this mathematically and figure out, well, what direction is it really going? All right, and so the fundamental tenet is still the same. That's what I had on that first slide at the beginning of the video. Is that the conservation of momentum says that momentum is conserved in all dimensions. So the total x momentum is going to be the same before and after. The total y momentum is going to be the same before and after. So now that we have our picture drawn, let's actually examine what the total momentum is. Again, I'm always encouraging at the beginning of these problems, just find the total momentum is what you want to do at the beginning. So let's see what's happened to the total momentum on the left side here. Total x momentum is going to be, let's say, let's go and label these real quick, A and B. All right. So it's going to be the x momentum of A plus the x momentum of B. Now at this point, you should be pretty confident this thing has no x momentum. If there was an angle, though, which I think there will be on the practice, if there's an angle, then you need to break that up, and then there would be some x momentum. But clearly, this thing has no x momentum, so we're not going to worry about that and just put in 0 for this piece. Plus, this piece does have x momentum. And we can see that it's 5 times 3, and be careful, this is to the left, so it's negative 3, gives me negative 15. And I can do that. The total x momentum is simply, I'll put pxt for total, is going to be negative 15 kilogram meter per second. Great. Now let's find the y momentum, and we're done finding totals. So py total is going to be fairly similar. The idea is A does have y momentum. Obviously, it's all y momentum. But B has no y momentum. It's moving to the left, but it's not moving up or down. So it's going to be 2 times 2 is 4 plus 5 times 0 is 0. You have 4 kilogram meter per second. Now afterwards, what I know is that the total x momentum still has to be negative 15. The total y momentum still has to be positive 4. And since those are the only two momentum, since I guess this is the only source of momentum, right? There's only one object now. All that means is that this thing has to have an x component. I want to draw that in red. Hold on. Just to keep my color straight. This thing has an x momentum of 15, or negative 15. I'm just going to write 15 here. I know that it's negative because it's going to the left, but it's kind of weird to put distances in negative, even though they technically are. So I'm just going to put that there, 15. And then y momentum has to be 4. So this side of the triangle has to be 4. And hey, this is going to be really easy. Because now you have two sides of the triangle, you just need the other. So find the velocity in your slab. Alright, so we've got to figure out the velocity is going to be, well, we have to use Pythagorean Theorem. So I'm going to use a squared plus b squared is c squared. So the square root of 4 squared plus 15 squared tells me is 15.5. Again, just like on those last problems, though, this 15.5 is not the velocity. This 15.5 is the momentum, right? It's 15.5 kilogram meter per second. So if I want to actually get the velocity, all I have to do is divide by the mass, and that's coming from P equals mv, right? Momentum is mass times velocity. If I want velocity, I have to divide both sides by m to get v by itself. And so velocity is just momentum divided by mass. So here is velocity is going to be 15.5 divided by the mass is, well, it's 7 now. So 15.5 divided by 7 gives me 2.2 meters per second. And that's the velocity. So you see, hopefully you see this one's a lot easier. Again, it still builds on those fundamental concepts though. What's the total x? What's the total y? If that's what it is before, and then it has to be that afterwards, that's the conservation of momentum. And then, well, if this has to be 4, this has to be 15, you know, you can figure out the rest. Now, I didn't ask on here, but I'm going to add, what is the angle? What is theta, real quick? Just because, again, it's the exact same idea. You have the three sides. You can use sine, cosine, or tangent. Personally, I'm a fan of just using inverse tangent because it just is probably the... You don't have to round anything, right? We rounded this, but these aren't rounded. So the angle is going to be the inverse tangent of opposite over adjacent is 4 over 15. So if I take the inverse tangent of 4 over 15, I get 14.9 degrees. So, oops, and I didn't, well, yeah. So theta is going to be 14.9 degrees. There you go. So hopefully you see that these are a lot, I think they're a lot easier than the elastic collisions. So since we started out with the two-dimensional elastic collisions, the inelastic collisions should be fairly simple. Thanks for watching.